Okay. Good, good. How was your guys' weekend? Did anything fun happen? No. Well, you're still alive. You're here. That is definitely exciting. Kind of on that note, I just want to talk about the fact that we are kind of officially at the point of the semester where it feels like a million things are happening all at once and chaos is always ensuing, and it's just kind of stressful. And that is okay. It is okay to feel stressed. But I also just want to kind of remind all of you guys of the importance of physically taking care of yourself. So make sure that you are drinking water and eating food at like regularly scheduled intervals and sleeping. I know that those are, that might kind of seem obvious to say, but it is also really, really, really easy to skip out on sleeping or skip out on eating a meal or go a whole day without drinking water. Also, like making sure that you are going out into the outside world and like moving, even if you just go outside and like walk around the block, that's really important to help kind of like clear your mind, give yourself a break from thinking. It is worth it, it is valuable, and just it doesn't matter how much you have to do. Like that is something that should be a priority. So, additionally, kind of to talk about exam one, I've had a lot of you guys contact me. Some of you guys I have replied to, some of you guys I have not replied to yet, about study strategies for kind of the upcoming exams. Yesterday, I typed out a document with essentially everything I did to study for exam one, and I emailed that to all of you, I think. I emailed that, right? Yes, yes. Okay, I have not. I emailed that to all of you. So definitely, if you want to use that as a resource, if you want to read through that, go ahead and check that out. Other than that, we can definitely talk about kind of more study skills in office hours. If you want to have a one-on-one meeting with me, last week was my crazy hectic week, so this week is a little bit more chill. So definitely let me know. And I'm sorry that I had Wi-Fi issues yesterday and I wasn't able to do office hours. But if you didn't see my email, I will be extending Tuesday's office hours from 5 till 7 to kind of make up for that lost time. Other than that, I sent out the Google form for class today to all of you through email, I don't know, like a couple hours ago. So definitely go ahead and fill that out at some point. And I think that's all the logistical things I want to know, unless anybody has any questions about anything. No. Okay, cool. So today we're going to talk about SN2. In particular, we're going to focus on the leaving group and the electrophile. The lecture video for today talks about the nucleophile. So if you've watched that already and you have that knowledge, totally great. If you haven't watched that yet, then it's fine. I don't expect you to have watched it yet. So kind of going off of that, on this next slide, I feel like there is some misunderstanding with when my office hours are. So something I'm going to try to do is just continuously keep like a running list of my upcoming office hours. Just at the beginning of my lecture notes, so that way you guys have it for reference. The next exam is on March 26th. Whoa, that was like really trippy because I was looking at both screens at once and I was like, how do I move my mouse? Okay, we're good now. The next exam is on March 26th, which is, oh my goodness, happy March, everyone. Today's March 1st. Minorly terrified. I don't really know how I'm gonna graduate in like 2 months, but it's gonna happen. But anyway, happy March. That means that we have 25 days until exam 2, so that's good. That's a good amount of time. You like that? Okay. So what we're going to do during class today is we are going to go over this problem right here. I copied it directly from Axelson's extra practice worksheets. The problem reads, for the SN2 reaction shown below, circle the leaving group, label the nucleophile, label the electrophile, provide the HOMO, provide the LUMO, and draw the product form. That's all assuming that there is a reaction that takes place. So this is a big problem. There's like 8 things you have to do. Like, I don't know, that's ridiculous. But we're gonna go ahead and we are going to work through it together. We're gonna talk through it together. But I'm going to give all of you guys a chance to think about it first, to process it, go ahead and start to write down some ideas for about 5 minutes, and then we will transition into going over it together as a class. Also, I'm gonna go fill up my water real quick, so don't like do anything horrible while I'm not here. All right, we'll probably give it a minute or so before we come back together. All right, so what are we thinking? Do we have any thoughts occurring? First of all, what is SN2? Like, what does that even stand for? Does that mean anything? So just letters and numbers? Substitution. What about the 2? Yeah, or bimolecular or second order. So SN2 stands for substitution with a nucleophile that is second order. So much like what we talked about last week with radical halogenation, we can get a pretty decent amount of information just from the name of the reaction. We know that this is a substitution. So what is a substitution reaction? What does it mean to substitute something? This is not a trick question. It just means that we're going to take one thing and replace it with another. So we're going to take out one leaving group and we're going to replace it with a nucleophile. And then we see that it's second order. What does that mean? Do we care that it's second order? Is that relevant? Okay, why? Yeah, so it's telling you the rate of the reaction is second order. And what that means, generally speaking, is it means that two things will collide in the rate determining step. It's 2 because it's second order. And we can say that rate is equal to the concentration of electrophile leaving group times the concentration of nucleophile. So it is relevant, and it's relevant because it tells us what the rate of the reaction depends on. So the rate of the reaction is not only going to depend on the characteristics, the qualities, the concentration of the electrophile, but it also depends on the nucleophile as well. So we have that. We have like a general framework for what's happening with SN2. So we can go ahead and kind of dive into this problem. The first thing that we have to do is we have to find the leaving group. What is the leaving group? Like if you were to give me a definition for what the term leaving group means, what is the leaving group? This is also not a trick. Yes, the leaving group is the group that leaves. So if you have to find the leaving group, you want to find whatever's going to leave. That's kind of the first part. Second part is, how do I know what the leaving group is going to be? Does anybody have any idea what the leaving group is for this problem? Or are we all like, bro, I don't know what's happening? Yeah, so it's going to be the one that the nucleophile kicks out. Does anybody know in particular what the nucleophile is going to kick out for this one? Iodine. Yeah. See, iodine is our leaving group. So, how did you know that? Yeah, Rachel? Yeah, so that is a valid reason, is halogens are typically leaving groups. Does anybody have anything else they want to add to that? Yeah?
It's associated with a strong,
Perfect. That is a good reasoning. And let's kind of like break that logic down a little bit. She said that iodine is associated with a strong acid. And when we're saying that iodine is associated with a strong acid, that doesn't mean like in this reaction it is. Generally speaking, we know that HI is a strong acid. So if HI is a strong acid, we know that if you have a strong acid, the associated base is going to be weak. So we know that I minus is going to be a weak conjugate base. And if we want to add on kind of one more layer onto this, we can talk about what I wrote on the board last week, where if something is weaker, it's going to be less reactive, it's going to be more stable, it's going to be lower in energy. So what we can do here is we can say that we know that since I minus is a weak conjugate base, it's going to be the leaving group because we want our leaving groups to be stable on their own. Our leaving groups are not dependent on the electrophile at all. They're able to exist on their own. They're able to be stable. They're calm. They're happy. So good leaving groups are going to be stable conjugate bases. This is always true. Does this make sense? Yes. I'm having some nods. Okay. Perfect. So we did a thing. We did the first step. The next thing is we want to label the nucleophile and the electrophile. What's the nucleophile? What is a nucleophile? If you were to define for me what a nucleophile is, what would you say? It's okay, guys. You don't have to worry because I have a definition for it. So the nucleophile, if we break this word down, the suffix phile means loves. So the nucleophile loves the nucleus. So what does that mean? What does it mean that the nucleophile loves the nucleus? Well, if the nucleophile loves the nucleus, we know that the nucleus is positively charged, which means that it loves things that are positively charged. If you love things that are positively charged, then you are going to be negatively charged. So the nucleophile is negatively charged. It's going to have a high electron density. In particular, the nucleophile, the best nucleophiles are always negatively charged, but you can have neutral nucleophiles. Neutral nucleophiles just need to have a lone pair. You need to have some electrons that you can use to attack, because the nucleophile is what attacks. So in this case, which of these two is the nucleophile? Yep, Cn minus is going to be our nucleophile. Why did you say Cn minus instead of saying NaCN? Say it again, sorry. Yeah, so with sodium is a spectator ion. That's the language that we use in Chem 102. In Orgo, we often call it a counter ion. Basically, both of those mean that the sodium does not matter. So some people are really upset about this, like they like to make sure that all atoms like are included in the balanced reaction. They don't like to like forget about anyone. But like I'm telling you that it is legit okay for us to just ignore sodium. This is an ionic compound. This is a salt. So since it is a salt, an ionic compound, that is how we know that that sodium is a counter ion. So we're going to take a break and I'm going to erase some things just because there's a lot going on. And we're going to again write that this is our nucleophile. And that means that this guy is going to have to be our electrophile. Similarly, phile means loves. So the electrophile loves electrons, which means that the electrophile is going to have a more positive charge to it. So how do we feel about that? Yes.
So is the nucleophile the NaCN or just the CN?
I don't think it matters per se. I think that saying that the nucleophile is Cn minus would be more correct, but I don't think it's wrong to say that NaCN is the nucleophile. So we got this situation going on right here. Is the leaving group always associated with the electrophile, or can you have the leaving group attached to the nucleophile? It's always. The leaving group and the electrophile are one. You're not going to have the leaving group attached to the nucleophile. That's wrong. That's horrible. That's the worst thing in the universe. So leaving group is always going to attach to the electrophile. So we have to talk about the HOMO and the LUMO, which is horrible because like molecular orbital theory was exam 1. So Axelson really just had the audacity to be like, no, you need to know what HOMO and LUMO mean again. So let's start there. What's the definition for HOMO? That was seriously, that sounded like music, honestly. HOMO is the highest occupied molecular orbital. LUMO is the lowest unoccupied molecular orbital. Now, we're going to kind of talk about this in detail because a lot of people get hung up on this, and there's actually a relatively easy, it's actually not that scary, not that spooky at all to identify the HOMO and the LUMO. So the HOMO is always associated with the nucleophile. Always. If we're talking about the HOMO, we're talking about the nucleophile. And the way I'm horrible at memorizing things. So I like to always have like a rational thought process that helps me get through. So with the HOMO, we're talking about an occupied orbital, which if it's occupied, that means it has electrons there, right? So if we're talking about an occupied orbital that has electrons, well, we need electrons to have, our nucleophile needs to have electrons to attack. So that's how I know the HOMO is always associated with the nucleophile. The LUMO, on the other hand, is unoccupied, which means that there's not a lone pair, there's no electrons present to attack because it's unoccupied, it's empty, which is why that's associated with the electrophile. Does that logic kind of make sense? Anybody have any questions yet? No? Okay, cool. So going off of that, does anybody know what the HOMO for the nucleophile would be? Say it again, sorry. Oh, sorry. It's so hard to tell who is talking because I don't know all of your voices yet. And you have a mask, so I don't see your mouth. Okay, does anybody have an idea? No? Yeah, Rachel? So SP is definitely going to be included in kind of defining our HOMO. But more generally, our HOMO is always going to be a lone pair when it comes to an SN2 reaction. So HOMOs are always going to be lone pairs for SN2. For SN2, the LUMO is always a sigma star anti-bonding orbital. And I'm putting these in boxes because that's important. Important stuff goes in boxes, apparently. Now the thing is that's generally speaking. So if you put this as an answer on an exam or on a discussion worksheet, it would be wrong because it's missing information. But these are always true. The HOMO always is a lone pair on the nucleophile, and the LUMO is always a sigma star orbital attached to the electrophile. But of course, I just saw that we need more information, so let's go a little bit more in depth. In particular, the HOMO is always the lone pair that does the attacking. It's the lone pair where you start your arrow pushing. It's the lone pair that has the greatest electron density. So in this case, what's going to be the, what atom's going to attack? Is the carbon going to attack or the nitrogen? Why? Yeah, because our carbon has that negative charge. So in particular for this problem, the HOMO is going to be the lone pair on the sp hybridized carbon atom of cyanide. Now this is a lot of things. We need to say that it's a lone pair. We need to say the hybridization of the atom. We need to say what the atom is. And we need to say that it's part of the nucleophile. But we see that it is a lone pair. The HOMO is always a lone pair. Whereas the LUMO is always going to be the bond between the alpha carbon and the leaving group. So let's kind of back that up for a second and talk about the alpha carbon. The alpha, saying a carbon is alpha, just means that it's right next to something else. So like in this case right here, we can say the carbon alpha to the leaving group means that it's the carbon that the leaving group is attached to. So that's why this carbon right here is the alpha carbon, because it's attached to the leaving group. Additionally, we could say like that the carbon that is 2 carbons away is like the beta carbon. Then we can say the gamma carbon. I don't know if there's something after gamma, but there might be. But anyway, we don't really care about that at all. This is just a terminology to describe like the carbon that's adjacent to the leaving group, the carbon that the leaving group is bound to. Does that make sense? Okay. So the LUMO is going to be the sigma star anti-bonding orbital of the carbon iodine bond. So it's always going to be the sigma star anti-binding orbital for whatever bond is being broken, which is always going to be the bond between the alpha carbon and the leaving group. How do we feel about that? Are these words making sense? Do we like these words? Yes, maybe. Okay, perfect. So, hey, we did three whole things. So we're gonna erase this. Also, just as a note, I am recording this. So it will be uploaded later to YouTube. In the case that you want to listen to me ramble on again, like I just wanted to provide that opportunity to all of you. So we have one thing left to do. Draw the products formed. Now, if we're drawing the products formed, we might as well go ahead and talk about the mechanism. So we're going to do that as well. So with SN2, it's concerted. What does concerted mean? Yeah. So concerted means that it happens in a single step. So radical halogenation, bro, that was like 200 steps, or maybe 3 or 4. But when it comes to SN2, this is concerted. It happens in one single step. So that's kind of the first layer. That's the first thing that we want to consider. So our arrow pushing is just going to be one step. That's it. Everything happens all at once. And in particular with SN2, we have what is called a backside attack. What that means, what a backside attack means, is it means that our nucleophile is going to attack on the opposite side of our leaving group. And our leaving group is going to leave. Now, what is the significance of the backside attack? Why do I care that there's a backside attack? Yes. So the backside attack means that I have an inversion of stereochemistry. Now we're going to pause for a second right here. We're going to pause because there was, it's a little bit tricky trying to understand when you will have a, when an inversion will result in a change in stereochemistry. So I know that somewhere in the lecture videos, Axelson mentioned that you will not always have an inversion of stereochemistry with SN2. And just to kind of clarify that, that is because if you don't have a stereocenter, if your alpha carbon is not a stereocenter, you can't have inversion. So anytime your alpha carbon is a stereocenter, you will have an inversion of stereochemistry. But if it's not a stereocenter, you can't switch the stereochemistry. Does that make sense? So like this guy right here, this alpha carbon is not a stereocenter, so you won't change the stereochemistry. In the case that we're dealing with here, this is a stereocenter. Whoops, that was supposed to be wedge. Let's make that wedge. So this is a stereocenter. So what that means is we are definitely going to have an inversion of stereochemistry. Generally speaking, when we say we're going to have an inversion of stereochemistry, that means that our stereochemistry is going to change from either R to S or S to R. So we don't have to do this, but just for the sake of, I don't know, just for fun, we're going to go ahead and define R and S at the stereocenter. So it looks like we have 1, 2, 3. This looks like it's R, which means it's actually S because that hydrogen is wedged. So we know that the stereocenter is S right here, which tells us that in the products, my alpha carbon better be R, because I need to have an inversion of stereochemistry because it's SN2 at a stereocenter. Now we're going to kind of go over 2 different ways to draw the product produced, because I feel like there's some confusion, or at least in past semesters, there's normally confusion when it comes to how to kind of draw out all the atoms in respect to each other. So let's go ahead and I'm going to redraw this guy right here. And the first method that we're going to do is what to do if your leaving group is in the plane. So our leaving group is actually in the plane for the problem that we're dealing with here. Now, I do want to note that there are multiple ways that you can draw the products. So you can draw the products however you want, as long as you get that inversion of stereochemistry. The reason why I'm kind of making it making it more black and white and separating it into these 2 rules is because I know that a lot of times people like to have rules that always work. So that's why we're going over these rules, but there are other ways to do it. But these 2 will just always work. So if we have a case like we do right here, where our leaving group is in the plane, what we're going to want to do is when we draw our product molecule, we're going to want to attach it so that way it is directly opposite of the leaving group. And the best way to kind of visualize this is to think about the transition state. So if we think about the transition state for SN2, we know that our transition state is going to be sp2 hybridized. And we're going to have our leaving group and our cyanide kind of opposite of each other right here. So we're going to have something like this. So what happens is we want to kind of go, and when we draw our product, we want to leave all of the atoms in the same place. So we're going to get something like this right here. So this right here is a correct way to draw our product. It looks a little bit unusual. It might not be how we would normally draw it, but right here, this product does show a retention in an inversion of stereochemistry, and we can prove that to ourselves. So here we have 1, 2, 3. So if we have 1, 2, 3, it looks like it's S, but because that hydrogen is wedged, it's actually going to be R. So that's one way that we can draw this inversion of stereochemistry. How do we feel about that? I'm getting very few responses. Let's do thumbs up, thumbs down, thumbs sideways. Do we understand what's happening? Do we not understand? Okay. Got some mixed results. Does anybody have any questions on this, or do we just need to sit with it a little longer? Okay. Yeah, Rachel? Yeah, so we're going to go over that way in just a second. So let's go ahead and erase this. The second way that we can do this in its easiest, or in order to do this, we need to have our leaving group be either wedged or dashed. Now the thing is with our leaving group right now, it's in the plane. So in order to use this second technique, we need to rotate our molecule. We need to rotate it such that our leaving group becomes either wedged or dashed. So when we rotate it, let's go ahead and make our iodine dashed, make our methyl wedged, and then we can put this hydrogen in the plane. So by rotating this, I'm not changing what the molecule is at all. I'm not changing the composition of the molecule. I am just I'm just rotating around this particular atom right here. So these two guys are the same molecule. One way I can prove to myself that they are the same molecule is I can make sure that the stereochemistry stayed the same. So 1, 2, 3. So if I have I would actually have to re-rotate it, wouldn't I? And then you would just get that same original molecule. So that would kind of be pointless. So I guess you just have to trust yourself. You have to trust your instinct that you did do the inversion correctly. But anyway, or the rotation correctly. So what we can do is if our leaving group is either wedged or dashed, this is the easier case. We love this. We love when this happens. What we can do here is we just will flip the stereochemistry. So in this case, my leaving group is dashed. So I want my nucleophile to be wedged. So we're going to see something like this. Now, the reason why I included the first case is that sometimes it can be tricky to rotate molecules around an atom. It's really easy to make mistakes, especially when you are just, especially when you're rushed and you're on an exam. So there are these two strategies that can be used that hopefully are beneficial to you all. So how do we feel about this? Do we have any other questions on this problem? Good, I think that we dissected this as far as we can dissect it. Yes, Kirkland?
So, for example, if they have something like this on the exam and they have the multiple choice, like pick the product, do you know if Apple prefers to use the wedge dash method or the in the plain method?
Yeah, so the question was if you were to have to like pick the product on a multiple choice, if Axelson would be more likely to use the wedge dash method or the in the plain method. And the truth is that Axelson is probably going to do something that is hard, and you have to like rotate the molecule, and it doesn't perfectly align with any of the other choices. Or she could give you one of the products that you would create from one of these methods. There's really like there's no telling what's going to happen. It just something will happen. Yes.
So this way, then don't you have to still make the hydrogen be the snap?
To determine RNS, yes.
Yeah.
Now normally we don't like determine RNS unless it's like unless you just want to like double check your work. But like normally she won't be like, what is the RNS configuration of the products? But yes, that's why for this particular example, it would be easiest to use the in the plain method, because otherwise to determine RNS, you would just have to like flip back and forth. But you can do whatever your heart tells you, whatever you desire is totally cool. Okay. So on that note, does anybody have any more questions? All right. So what we're gonna do is I'm gonna go ahead and stop sharing my screen. Then you guys can separate out into groups and person. I'll put the people on Zoom into a breakout room and get the worksheets ready. And then you guys are free to kind of work with those for the rest of class today. I'll actually get the worksheets ready first, so that way you can grab those while I'm putting people into breakout rooms.